Hello.
Can start.
Okay. Shall I start?
Yeah.
Okay. Yeah. Hello everyone. Good evening. Actually, today I will give you the lectures over the analog layout, an overview gesture of the analog layout. What is that thing? How we're going to cover up in the upcoming sessions and everything. So, starting with here. So, contents are actually in analog layout are analog layout and its flow. This is the agenda of today's meeting. Flow, then coming with the floor plan. Actually, starting with the floor plan only, we get schematic. After that, we get the do the floor planning. Then placement based DRC matching, routing, LVS DRC, and the analog layout concepts means all the basic fundamental what issues, what are the prevention of those issues we need to take care while doing the layout. In this process only, in the time of placement and routing, we do much concept of the EMIR, crosstalk, means shieldings are there. So we need to take care of them. So those are the analog concepts with fabrication, memory layout, and standard layout. So this is the agenda of today's meeting. So starting with the floor plan. So with the analog layout flow, if I start, so this is the actual whole hierarchy of the analog layout flow in which we start from floor plan and end with tape out, which goes to fabrication after post layout simulation. So first floor plan we do. Floor plan means if you come to the floor plan, the definition of the floor plan is the area required to place the analog block means suppose this is an area. Okay. So in this area, suppose you have an X area and this is a Y. Suppose if you are taking this area, in this area we need to place this. This is one differential. Suppose this is a block. Suppose you get a piece of land, okay, of X by Y square feet, and you need to put one 3 bedrooms, one kitchen, one hall dining, and all sorts of requirement of your home, how to you build your home. You have to plan this according to this area. So that's actually the same concept here in floor plan we do. So here are the capacitors. You can see some blocks are there, some critical blocks, current mirror, diff pair, all sorts of blocks are present inside this floor plan. Once a floor plan is done, the area is fixed. It cannot be changed. We have to plan the floor plan in such a way that the device completely fits. It should be reliable. It should be quality. It should be passing the design rule checks. LVS, delay of the signal should be minimal in this one, because if we do long routings, for the critical nets, it will be, the delay will increase, of course. So we need to make it somehow that should be quality and optimized, so that there should not be any problem after the, if other floor plan happens, it is irreversible and it's a rework again done to be done, which quite time taking and not cost effective also. Hello. Okay. Yes. So in the floor plan stage, we get from the schematic part. Suppose from the schematic part, this is about schematic. If you are taking, we are placing these kinds of schematic, transferring the schematic to layout format. In the layout format, we will do multiple techniques: matching, electromigration, IR drop. These concepts will come later. So this is the fundamental funda of the floor planning. Now coming to the placement, matching, and base DRC. We will look into the tool after this also. In the placement thing and half DRC, why it is done? Because when you are done with the floor plan, suppose in this area you have done the floor plan, right? So after doing the floor plan, the devices are fixed now. The area is now fixed. You cannot change the area. You have put the device. And one more thing, remember, while putting the devices should follow the signal flow of the schematic. Whatever the, suppose this is a signal flow. Okay, so this is one kind of block and it's another block. It's called a differential pair, this one, and it's called the current meter. So it should be actually aligned same to same as a schematic part. It should not be different because it will change. The signal flow will change the issue later. So in the placement stage, we actually do the placement matching. We will do because the matching is a essential part of the transistors matching part. So we'll do the matching part. Then we will be moving to the base DRC in which we check the distance between the N-well to N-well layers. There are lots of layers you will get to know later. There are multiple layers in the layout format. So N-well, metal one, polysilicon layer, then oxide layer. We check this kind of DRC, which is called base DRC or half DRC in the placement stage, where we will checking the distance. Suppose if you see this is one ending, this is called a guard ring, okay, and this is also another guard ring. Means this is the area of this block, this is the area of this block. So there should be a spacing between these two ending part of these blocks. Otherwise, it will be highlighting the DRC letter, which is not good. So later to be mess with the layout, we should always follow the base DRC, clean the base DRC, then go to the next stage. Before that, till the base DRC or half DRC is not clean, we should follow this one. So this is actually the stage of placement where we do matching and base DRC. These two things, putting the guard ring across the layout devices, blocks, and also then place it accordingly, the signal flow. So in the placement, and there's a matching part which has two kinds of matching. One is common centroid, one is interdigitization. Just to have a look overview, I'm just telling common centroid and interdigitization. We will discuss it later when we'll come in details of the matching, how matching is done, what are the patterns of matching, how in x-axis and y-axis we do. So we will able to do so. So this is the common centroid one. This is the common centroid matching, and this is the interdigitization matching. It's just a small discussion, so I'm not explaining the matching in much depth. Next, come to the base DRC. In this base DRC, as I told, we need to do the base DRC in the time of placement only, because to avoid messed up DRCs, lots of other DRC will come after the routing stage. When the routing stage is done, you should not get the base DRC error on that stage. If you get, means there is a lot of mess. If you get the base DRC, and if you suppose, I give an example. Suppose this is two block, okay, two block. If I suppose in this two block, this is at one distance and this is at one distance. There is some space between this one. This space is not according to the design rule checks, DRC check. So now you have done the routings. Okay, so the routings are done, kind of this routing is done. What will happen if you get DRC, this base DRC, don't clean here at this stage and you do it in a later stage, what will happen? You get DRC. And when you try to either move this device left or right, forward or backward, the spacing will obviously change here. If it change, then what will happen? The routing length of this metal will also change, which is not, which is a violation of the area also in floor plan. So this base DRC is very, very important at this stage. Next, we come to the routing. Routing means we are connecting each and block. Suppose in this area, there are multiple blocks, one block, two block. So there are multiple blocks here. So these are all blocks done with a floor plan and base DRC clean. Now, if we do the routing, we need to connect this block. Suppose we have to connect each and every block. One block will be here. This is the connection of the block, putting the power planning. We have to do the power planning also here, like VDD here, the VSS here, or kind of power mesh also we do here. This kind of power mesh also we follow. So in this stage of routing, we need to take care of all sorts of things, and DRC should be also clean for this routing stage. The goal of the routing should be connections are made between signals and metal layers, and it should be minimal, because if the routing lengths are higher, then you might get connected to the gate, then you might get antenna effect kind of violation, then electromigration you will get, major thing you will get IR drop. These all kinds of issue you might get. So it should, the routing always should follow these kinds of violation, prevent these kinds of violation, and it should not, this violation should not be there in that routing stage. It should be clean and quality routing should be there. Now coming to the DRC part. In the DRC part, there we will check the routing stage. This is the routing stage DRC. We will, in this one, we check the metal width, metal 1 to the higher metals, any of the metal, different technologies, different metals. We will be checking different metal structures, metal density, we will able to, we will get the things, and many other DRC errors we will able to get. So see, these are the types of DRC: minimum width spacing of metal, the via width and spacings, minimum area, shots violation. These kinds of DRC we generally get in the DRC stage. You will able to see the common, see, these are the common DRC. This is a test case has been created, in which you can see these are the pass case, the fail case, in which you can see in the fail case, of course, the DRC spacings are less. So that's why it's not according to the DRM, design rule manual. That's why we are getting violation at this area, and this area is passing, and this area is failing. So that's why we are getting these errors. You can see metals actually floating metals we are getting. Then we are getting CT layers. There are multiple layers. These kinds of DRC we will getting at this stage. Now coming to the LVS part. LVS, what we do, we have designed a schematic. The schematic designer has done the routings and every sorts of thing and every structure they have done. And after that schematic is completed, reviewed, and passed all the technical possibilities, it will come to the layout stage. You are done with the layout, floor planning, base, DRC placement, routing, every DRC is clean. The goal of LVS is to that we have drawn the layout, is that layout connections on all sorts of the designs, like extractions, then the connections are according to the schematic or not. If it is not with the schematic, it will fail the LVS. If it is according to the schematic, it will pass the LVS. So the goal of the LVS is to compare the schematic with the layout. So it's full form is the layout versus schematic. So in this one, what we do, we take the net list of the schematic. We get the schematic net list here. So suppose this is a net list with node points actually defined in spice format actually. So we get the net list of the schematic, we generate it from the tool. Then we take the layout extraction file. We put it in the comparison tool. It will compare the connections of the layout with the schematic, and it will give the result of the LVS. This is what actually, if just I tell you, a architecture has drawn one land and home structure, like one washroom, kitchen, bedroom, like hall dining, balcony, all sorts of in a map. That's the schematic. Now we are now the engineer has drawn made this. Excuse me. The engineers have now made the home, okay, structure, but it should be according to the architecture which has been passed by the government, local bodies, which is a schematic engineer here also we do. It should actually pass that that thing. The home should be according to the architectural plan. So that is the same concept here we use at LVS. That's where comparing it's actually or not. If it's not, then we have to do rework. If it is not, we have to fix this violation. If it is okay, pass, then fine. So this is related to the LVS thing actually. So these are the kind of common LVS issue we get. Like open nets, let's suppose a net is open between two point A and B, then extraction error, then some device property mismatch will also you get. Some schematic has a W by L is suppose 800 nanometer by 800 nanometer by 400 nanometer suppose, but in the layout it is some different parameter is there, like it become 400 by 500, then it's a mismatch na. Then that is actually these are the common DRC error we generally get. Property error, port not present there, uh, the device names are not present there. Those kinds of error we can get in the LVS issue. So after the LVS issue is done, so we go to the post layout simulation, which will be done by the we generate the left cell, which is done. Go to the schematic engineer. They will do the post layout simulation, or sometimes layout engineer also do that one. They will check if it is okay as per the schematic. It will go to tape out. That's all the overall view of the analog layout. So which we actually saw in the this PPT. Floor plan, placement based DRC, routing, DRC LVS, post layout simulation, and tape out. This is the complete overview of the analog layout flow. Now, in between, while routing is done, we check lots of checks. Like lot of physics is there, which is like electromigration one. Very common, can be found in many of the circuits, which is it's completely itself a big topic which to be covered in the concept earlier. The IR draw, which is the Ohm's law also, actually there it's a Ohm's law only. Then antenna effect in the part of gate connection. Suppose I just give you a brief of antenna effect. Suppose this is a gate, okay. We have a metal length of this much. Okay, metal this much. When the fabrication will be done, some kind of some charges get stored in these metal layers. Okay, these metal layers are connected to the gate. These charges, when get strike to the gate actually of the transistor, either it will damage the device or it will change the parameter of the devices. Okay, suppose the device may work more faster, device may work slower, not according to our requirement. So this is antenna effect, which should be avoided and which is calculated as per the formula given in the DRM as per the technology. So to avoid this, we put a diode near to the end of the gate. Because why end of the gate? Because the all charges inside this gate should come and get drained. If you put air, then it will drain up till here. Then this area will remain. It will damage. So we put at least as least end of the metal length of the to prevent the antenna effect. This is a small brief of the antenna effect. Then crosstalk we will work shielding, in which coaxial shielding, sidewall shielding, tandem, multiple that mainly we use crosstalk and sidewall shielding. This kind of shielding we generally use. Then concept of deep end will come, latch up will come, in which to prevent guarding is used. Well proximity effect will use, shallow trench isolation will use. Currently in the technology we are using shallow trench isolation. In FinFETs we are using fin trench isolation. Earlier we used to do locus, which is now not used anymore. We on that place of locus in planar devices we use STI, shallow trench isolation. In the lower nodes in FinFET we use fin trench isolation. Then short channel effect will come into picture, length of diffusion. These all are the concepts of the analog layout. These are concepts we will be covering in later stage each topic will be covering in a proper way, and which will be shown in the tool also, that how these are being implemented when you are working as a layout engineer in the industry. Then standard cell layout, memory layout, these are the part of the analog layout. Then some blocks we will be taking care, BGR, amplifier, LDO, ADC, these all kinds of analog blocks. See, these are the blocks. In these kinds of blocks, any block, these kinds of error will come. These kinds of error will come. These kinds of issue will come. We have to prevent them. We have to do these kinds of error. We have to prevent them. And this CMOS fabrication. In CMOS fabrication, many things will be there. Fabrication of the MOSFET, BJT, then FDSOI, silicon and insulator, then FinFET fabrication, twin tub fabrication, multiple fabrication we will be able to see. Then one new and very relevant actually technology in the market is a power management device company used. Those are called BCD nodes, in which bipolar, CMOS and LDMOS, three things are fabricated in a single wafer, so that we can arrange the power. The power management company use these kinds of nodes. We will be talking this in the time of CMOS fabrication and all sorts of things. So this is the end of this analog layout up till concepts and flow. Now we will go to the tool once to see how we able to create a layout. Because without knowing the tool knowledge, this kinds of bookish knowledge is not enough. We have to implement this bookish knowledge in the industry. Hello. Hello. Hello.
Hello, sir.
Yeah, I can. Okay. Now I'm going to the tool actually. Can you all guys see the tool? Hello, can you all guys see the tool?
No, sir.
Yeah, now?
Yes, sir, we can see the tool.
Okay. Okay. So I just do one thing for you. So this is the tool actually here. Let me open the terminal. I have created all the actually that folders. We will show the creation of folders and all sorts of work area in a later stage. I'm just running the tool once. First, this is the overview of the tool. First, this is the view. This is called CWI window, this one. And that's the terminal. In the terminal, you need to create your directory and all sorts of things. You will create here, you will get your work directory here, you have to create. Then you have to run this one tool. And this is a 90 nanometer technology we will be using. Excuse me. This is called the CWI window. So in this one, there are multiple options you will be able to see. Files, where you can do import, export, refresh, tools, options, help. So for the time being, we will be using this library manager. So many things are there we will be able to use later. So library manager will use it. Going to the library manager, this is the view of the library manager, where this is the library part, this is the cell, this is the view. Here you will create the library. Suppose a major library is there, in that one multiple, suppose there is a block name called as memory block, DDR. Here we will name the file as DDR at this part, a library part, we will have a DDR name. It's a block, just think it's a block. After this DDR, there will be multiple cells, like SRAM cell, other kinds of cell also there. DDR doesn't contain SRAM. So multiple cells like memory controller, then sense amplifier, many cells will be there, which will be completely here at this cell level, where we will do the integration also we can able to do in this one. So, and here you will get the view. Suppose we are clicking one of the cell here. Okay, so you are getting symbol, Verilog. These are the view, actually what view you want. You want a schematic view, you want a layout view, you want a symbol view, you can get all these sorts of thing here. So coming with this one here, we will able to, okay. Let me do one thing for you. Let me create a see. Now we will go to file. In the file, if we go and it's new, okay, you will get library. Okay, here you can create any of the library if you want. So I am creating a cell view here actually. In this new library I am making. I'm making it as a test underscore inverter. Okay. It has been created. This test underscore has been created, and you will get one pop-up like this one. We have to attach the technology file here. We have to click this attach to an existing technology library. You have to click OK. After going here, you will get to see here is we are using 90 nanometer, GPDK 90 nanometer. When you are using TSMC library, UMC, Intel, Global Foundry, Samsung, that name will be highlighting here. These are different things. You have to be click on this technology thing. GPDK here using GPDK 90, so using this one. Okay. So now this 90 nanometer technology is attached with this test underscore inverter. Okay. I have created one. I just put it there. Okay. Okay. So I have already created one inverter thing. So this is a schematic. So in this one, if you go now, you have to go here after clicking. Suppose you have created this library. Okay. After when the library is created, click on this one. Go to the file manager. Click on cell view. Cell view is done. Now I'm making name as a layout underscore inverter underscore one. Okay. We put OK here. After this OK is there in the cell view, it will open the schematic for you. It will open actually the schematic for you here. In this schematic, you need to make your schematic file. Means you have to make your schematic here. Now to make schematic, it's a part of an analog circuit design study. So you will be studying all this circuit design in the analog circuit design part. It's design of the schematic, how schematic is designed, how it is this simulation is done. I just give you a brief of the schematic. After the schematic window is open completely like this, click on this. You can see one MOSFET kind of thing is there. Okay, it can create instance. Its name is. It's like a MOSFET symbol. So click on that one. You will able to browse. Go to that GPDK 90. You will see NMOS 1 volt, NMOS 1B underscore 3. There are multiple voltages NMOS are there. I'm taking in 1 volt. Now click on that one. See, I show you view. See here view is there. You have to go to the symbol only symbol. Height, put it here. Go to that again. Browse. Search for the PMOS 1 volt. Okay. Put it here. Now, this is the schematic we have got. Take this one. This is the wire. Okay. And to fit this window, suppose I am small in this size. To fit this window, you have to press F, only F button keyboard. It will fit the window. After going to this is the wire connection. Okay. In the wire connection, we have to connect these devices. We have to use wire connection. Create narrow wire. Connect this one. Because inverter schematic looks like this. Connect this. Suppose source, gate, drain, gate, source. So source, gate, drain, and drain of PMOS, drain of NMOS is getting connected. Gates are connected here. These are bulks. PMOS bulk will be connected to the VDD. NMOS bulk will be connected to the VSS. And from this between drain to drain connection, we'll pull one wire, will be output. Here from gate to gate, we'll pull one wire, will be input. After this, we have to put the create pins. After putting the create pin here, we have to rename the pin. What pin? We are doing the input pin first, in as name. Direction of the pin should be input, output. You have to take care of this one. So direction of the input pin, take this one, connect it. Again, go to this one, out pin. I need now. Output pin. So this is the output pin now. So now to the, we are doing the layout. So we have to put the bidirectional pin, input, output, both for the VDD and VSS. Otherwise, we will not able to connect, get the pins in the layout. So we have to do it here in. So we are doing as a VDD and change it as input, output. Put it here. Again, VSS, input, output, put it below. Connect this now. This also connected. So this is the overall schematic of the inverter. Okay. So now this is done. We have done this schematic inverter. Save it, run check save. Now no error is there. Go to the launch option. This here will get a launch option here. You will get multiple. If you want to do simulation, you have to do ADL, Excel. We can connect the power source here, pulse source. We have to put the probe here. We have to check the output waveform. We will now concentrating with the layout part. So going to the layout here, we click on layout Excel. Layout Excel there, you will get a startup option like pop-up like this. Create new, configuration also create new, we put. Okay, press OK. The cell name is inverter 1, view layout, and the type is also layout. Now we press OK. It will generate this one. Now we enlarge this window first. This is the view of the layout editor window, where here you get this kind of tools are for flipping, rotating. The movement tools are there here, and these are some of the tools you will be using. Partial selection, non-partial selection. Then align tool is also there. You will get an align tool is there. See, align tool is also there. We'll able to align properly by putting the values here. These are the file, edit. You will get verify, create. You have to put guard rings, all sorts of things. Then going to floor plan. This is the floor plan. This is not required at this stage. Asura, this is the verification where we do the LVS, DRC, and parasitic extractions, all sorts of things. Then these are the tool section, options here, connectivity is there. And left side, you will able to see these are the layer palette. Here able to see N-well, oxide, poly layer, then metal layers, VRs, all layers are there. You will able to see these layers here. And this is the object grid, object palette. Here you can turn on, off the visibility selection. You can do with the shapes, like one shape is there. You will able to freeze it. You don't want to select, don't click on deselect, it will be deselected. There's all many functions there. When you will working consistently on this tool, you will be mastering the tools more and more. So for the timing now, we are trying to just generate the schematic to the layout, where we told as a floor plan. So we will be doing now the floor plan. We have got the schematic. We got the schematic now. We have the schematic. We have to make it a floor plan now. So make a floor plan first. First press E option. In E option, if you press, you will get the editor windows display option, where you can fix set your grid. I am setting it as 005 here and 005 here. And all you should turn on the pin names. You can turn on everything you can do here. We have to fix the grid. If this is not done at this stage, later you might get a grid error in the DRC window. and which is not good after long floor plan layout and routing is done. So first it should be communicated with your industry guys, with your manager or lead. They will tell what the grid you need to follow for the particular technology. First and foremost, you should press E option, only E. Put the grid option here, align the grid, then press OK. You can change the resolutions also. I'm not changing resolution, so you can press OK here. Now the grid is fixed as 0.005. Now I am going to connectivity. See, shortcuts are also there, symbols are there. I am showing you from the connectivity tab. Okay, go to the connectivity tab, generate all from, see, these kind of symbols you will able to see at this stage also, at this area also. These are all from source, this is selected source. I just tell you the difference between all source and selected source. All source means if suppose there are many schematics are there. Okay, it's a huge schematic. There is a transistor, there is a transistor, many things are there. So if you generate it all from source at a certain time, everything will come here, every devices, which can be confusion for you. So better always try to select it as source, only select this part and transfer there. I just show you. If I click on connectivity, generate selected from source. Okay. I go here, I click this one, and it come to inverter. See, it came here for me. The PMOS devices came for me here. If I would have done all from source, see, now again I go here, I click on NMOS device. Came this one. Now you saw this selected by one you can do as per your convenience. If I delete this one now and I go to the all from source. Let me change its parameter once. Length is 400 by 800. Okay. And this one also I change it as 400 by 800. I make it like this. Okay. Now, if I do the all from source, I am doing, you have seen the selected from source one by one. Now, if I do all from source, this pop-up will come for you, generate layout. In this IO pin, if you go, after clicking on the all from source, you will get a generate layout in this stage. You will get a generate layout at this stage, all from source. In this one, you will get a IO pins. These IO pins should be, because there were pins, right? So these pins are there. See, in, out, VDD, VSS. See, in, out, VDD, this pin should be changed to metal 1 pins. You have to search here. See, here it's a metal 1 pin. Because there are metal 1 drawing, metal 1 pin. Metal 1 drawing is for metal connections. And metal 1 pin connect to the output signals. Means it will go to output, input and output signals, it will be going. You should be updating this one. No need to touch all these things. Okay, now click on generate. See, it has been generated. This one, see, pins are here, 4 pins, VDD basis in and out. PMOS, NMOS device there, and a PR boundary has automatically came for you. In the selected from source, you have to do it all this manually. Generating the device, generating the pins, and creating the PR boundary also. That can also be done. You will be able to see it in later stage. Now, you cannot see these layers. You cannot see these layers. To view this layer, you have to press Shift F. See, Shift F came here. You can now see the layers. Now this is a floor plan. This is a floor area you have got. It's a default. You can change it now. So it has some measurement. It has some measurement, right? it is some measurement 3.4 by roughly 3.4. Okay, so it has some measurement. I just pull this device. To pull this device, select both the device or individual device, press only S, and which is the stretch option, or you can put the M option, move option also, and pull it in the top. Put it here. Okay. Now, to decrease the area, you need to take it up till here. Here, done. So this is the stage of the floor plan where you will be deciding. So this is the area. Okay. And here we will be able to, now this area is fixed. You cannot change it anymore. In this one, this area is now fixed. We cannot change it anymore. This, because this area now actually has 1.24 by 3.4. Now this area is fixed. Your lead has been verifying this one with the customer or the lead. Done. You cannot change it anymore. Can't change it. Here you will able to, so some changes can be there. So you just for a safe side, make it a bit higher at this stage. Now this area is fixed. We see, once area is fixed, decrement can be there. If you want to optimize, you can more decrease the size, but you cannot increase it. Increasing is not allowed in the industry. But when you're decreasing also, you have to inform. So these are the two devices. As per the DRC, it should be aligned properly, which is the half DRC. Now, if I run the half DRC, if I get error, it is not good. So this is the devices. Now what happened? Now I take a metal one here connection. I draw one here. See, this is the VDD connection going in the top. So to draw this metal connection, press P option, only P. First select that metal here or what layer you want to draw. Press P and draw this one like this. See, it has been drawn like this. But you see, it is not aligned. Some technology is auto aligned. You will draw, it will automatically check this track only. But here it is not happening. So click on this layer. Press A option, you say align option, and put it. It got aligned. See, okay. Same goes for this one also. I just copy it from the top. Okay, I had copied it from the top. Here also, we need to put one, because why I'm doing this one? This is the drain, and so this is the VDD, this is the VSS, and this is the drain and drain connection. We will be connecting this drain and drain for the output stage. We have done here. Take this one, align it. Align it, you will get it aligned. See, here it got aligned. The output is done. Here also this VDD VSS is done. See, now this green is the polysilicon layer. In this polysilicon layer, you cannot increase it. You should not increase, because it's a gate connection. It is a gate length, which is very crucial in this transistor. If you draw it manually, it might extend the gate length. Okay, so to avoid that one, you always should go to VIA option. To get VIA option, press option O. O for orange. Press O. Got create VIA. There are multiple single, stack, auto. So I'll be doing the single one here. Select VIA definition, what you want. We want M1 to poly layer. Means here M1 to poly layer, because M1 connection or the metal connection is the connection in which you will be connecting to the different devices or blocks. Poly is for the individual device. So M1 to poly layer we need here, selecting here. Rotate it, height, put it here. one put here, put one here. Okay. So align it properly. So you can align it properly. By aligning it, see, this has been drawn properly here. This is already there. Now what we can do, we can draw one metal from here. We have clicked this one metal one. Now already one metal, you can see one blue structure is there inside one layer. That's a metal one layer. Now if we draw this one, take it, align with, so the quality of the layer should be good. Now if I aligned it. Now I am just pulling these metals from the top. See, this here, this option is called partial selection. If I turn off this one, you will getting this completely. You won't be able to select at this area. To turn it on, only you want to stretch it, this one, pull and stretch it like this. Pull here and stretch it like this. Done. Now up till this part done. Now going till here, now we put the pins here. What is this pin? This is the output pin. Take this pin. Take this pin here and put it here. This is the output pin. This is the output connection. We put the output pin here. So let me know what is this pin. This is the input pin. So we take this input pin. See, it is highlighting that orange marker also. Okay. So you will and put it align here. Aligned. Now this is a VDD connection. We align it with this one also. And this is the VSS one. So and we align this one also. Okay, this one. Okay. Now up till here it is done. Pin connections are done, all sorts of things are done. Now we have to avoid the latch up and all sorts of things, we have to do put a multi-part path here. To do that one, I am doing it like this, Shift G. This is a PMOS. We need an N tap. We need a VDD connection, right? We are taking this one here. See, let me put VDD. VD. Let me scroll it here. Let me delete this part. We don't need. Okay. Modified. Okay, due to some reason, I don't think it is okay. Okay. Mm, okay, it got deleted. Now I take this part here and pull it up till here. Okay. And for this one also, Shift G, because there's a below is a P tab N type device, so P tab will be there. It's VSS hide, and we just put it like this. Now I pull it up to here. Now this has been till here. Now we have to align it. Now we have to align it up till here. This one also align it up till here. Now done. And this, there is an end well. Here is also an end well. Here is also an end well. Okay. To merge, connect them. See, you will get a also option here, AV, NV. So these are the options we can use to turn on individual layers. This is the visibility, this is the selection. If the visibility is turned off, if the visibility is turned off here, then it will not, it will see visibility is turned off and is the selection turned off. Selection turned off means you won't be able to select the layer, but visibility is turned off means you won't be able to visible the layers. And here you will be able to see one used layer. So whatever the layers we have used in this block, we will be able to see these used layers only. And this is the all layers, whatever the layer this PDK gives us, we will get these layers at this stage here. So now I have aligned it to do it like that, end well drawing. Okay, I will be putting NV, only turning on the end well. To turn on the end well, see, the end well to end well, here is a distance. It should not be there. Either you follow the maximum distance thing or you should align it. Otherwise, it will give a DRC error. Now I put all visible. Now it's not visible. Okay. Same goes for to align it like this. For this one also. For this one also. Okay. And after this is done, let me align this whole thing with the below structure. Okay. Now it got aligned up till here. This is also aligned up till here. Now this is now my floor plan is been, our floor plan is done. Routing is also done. So I have decreased the floor plan PR boundary. Now this is up till here connection is done. Now we put the names of those pins. It should be first going to this one, press L, only L option. L, select layer, first click on, make it as metal 1 pin. Make it as metal 1 pin first. Find the pin, metal 1 pin, this one. Make it as VDD here. Make it anything, stick, Roman, anything. This is the height, so it should not increase. Actually, it should be proper. Okay. So now we make it like 0.2. That's fine. Take it and put it over the this layer, because this pin should, and of course this pin always should be aligning the whole this structure. It should not be at the minimal stage. It should be aligning the whole thing. So that's why I am doing this one. And okay, now done this one for, and for this one also. I am connecting it here. This one also I am connecting it here. And this one pin, or this pin also I am aligning, pressing A option and aligning it here. Okay. So the name of this one is already done. We will put the name, this is the output pin. This is the input pin. We put L in name in. We gave it the input name. We put as an input pin, this one. Okay. Now we go to the L again, put the output pin, OUT out. Make it as an output pin. So better to make it the output pin, make it as 0.08, much better. Okay. Now it looks much more good. Delete it, again make it input 9. Yeah, now it's fine. Now here, go to VSS, again put here VSS, make it 0.08. 0.3. Point 3 and put it up till here. Now this is the complete floor plan routing and everything. It's an inverter, so many concepts are not covered in this one. So when you go to the higher blocks, different kinds of analog blocks and mixed signal blocks, you will get to know more connections. This is the complete layout of an inverter. So it's actually it is called a standard cell also. We have not followed the many concepts. So this kind of block should be so much aligned. If suppose you have to make an array, suppose you have to make an array of this one. Okay, so then what will happen? You have to make it such a way that if you will instantiate this one, means again you have to make it in a different library. Suppose you're copying this one, suppose I'm copying this one here. It should actually very much aligned and even connected like this. It should be connected like this, but and still it should follow the DRC. Still it should follow the DRC and it should be connected in a complete proper manner, but it should not be violating any connection and DRC thing. This is the how array you have to able to create. So this is the layout. This is the layout of an inverter. Hope you guys have, this is almost for the today's session. Hope you guys all have learned these things and hope you guys enjoyed the session. Yes, now if I go here. Hello. 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 Hello.
Hello, sir. Hello, sir.
Yes. Yeah, hello.
Yeah.
Yeah, is it you are able to understand the session?
Yes, sir. Yes, sir. So beautiful session.
So yeah, any issue regarding the layout, you can ask me just now.
I mean, just it's a starting point, right, sir? Once we start, if we have any doubt, we can go through it.
Okay. No issue.
Nothing. Yeah. Sure.
Yeah, I think VLSI for all is in mute. So okay, I don't. Hi Rajat. Okay, guys.
Okay. So thank you so much. Thank you.
Yeah, hi. Hello.
Thank you,
The session is over.
Yeah.
So I hope you all have enjoyed the session.
Yeah. was
So yes, tell.
Yeah, it was amazing. It was good.
Actually, your sound is not audible to me.
Yeah,
Actually,
it was good. It was good.
Okay. Thank you.
Okay,
Okay.
fine. Okay. Thank you.
Okay. Bye. Good night, everyone.
Good.